On August 21st, 2019, NASA's NICER telescope on the International Space Station observed its brightest X-ray burst to date. The flare-up came from SACS J1808, a binary system about 11,000 light-years away. Here, a pulsar, a rapidly spinning neutron star, draws gas from its companion, an object called a brown dwarf that is larger than a planet but less massive than a star. Hydrogen gas from the brown dwarf forms an accretion disk around the pulsar. Every few years, the disk becomes unstable. This sends a rush of gas toward the pulsar that makes it brighten in X-rays. The pulsar's super-strong magnetic field sweeps up the gas and channels it to the object's surface. Hydrogen nuclei falling to the pulsar's surface fuse together, producing energy and forming helium nuclei, which settle out below. This process is similar to what happens inside our Sun. Then, when the conditions are just right, the entire helium layer ignites in a brief but intense thermonuclear fireball. Astronomers call this a Type 1 X-ray burst. Here's how it happened. The explosion first blows off the hydrogen layer, which expands and ultimately dissipates. Then, the rising radiation builds to the point where it blows off the helium layer, which overtakes the hydrogen shell. Some of the X-rays emitted in the blast scatter off of the accretion disk. The fireball then quickly cools, and the helium settles back onto the surface. It was all over in 20 seconds, but NICER data clearly show important details that haven't been seen together in other bursts. This will help scientists better understand the extreme physics of these eruptions on accreting neutron stars.
Our planet Earth, the third of 8 planets in our solar system. Orbits once per year around our single sun. During the day, the sun is the only star we see in the sky. During the night, we can see countless other stars trillions of kilometers away. But wouldn't it be strange to look up at the sky and see 2 suns? Or maybe even more. In fact, systems with 2 or more stars aren't actually that uncommon. It's almost impossible to observe a binary system of stars with the naked eye, because the stars are usually very close together and appear to be shining from just a single point. In fact, more than 80% of all stars are members of multiple star systems containing 2 or more stars. The way binary systems are formed isn't completely known. We simply can't live long enough to see such an event unfold. However, the most likely way for a binary star system to form is actually during the star's birth. Stars form in giant gas clouds of dense interstellar gas, like the Omega and Eagle nebula. Gravity starts to pull the gas inwards and collapses it into a brand new star. Typically, a large star-forming region will produce many stars of different masses, and often these stars will interact with each other to form multi-star systems. How pairs of stars evolve is mainly based on the distance from one another. Wide binaries usually have no significant effect on each other, so they form independently. On the other hand, closer binaries can have a huge effect on one another, and even begin to transfer mass as they evolve and grow. The closest binary star system to us is the Alpha Centauri system. But at over 41 trillion kilometers away, I'm pretty happy right where I am. After all, the sun is a pretty beautiful thing.
20 years ago, the CSIRO Parkes Radio Telescope discovered a unique gravitational laboratory over 10,000 light-years away in the constellation Musca. The system comprised of a white dwarf, a few 100,000 times the mass and density of the Earth, and an exotic neutron star in the form of a pulsar, locked in a tight 5-hour orbit. Our team has been mapping the orbit of the pulsar in a series of campaigns since the early 2000s. We found that not only is the pulsar's orbit shrinking because of the emission of gravitational waves, its entire orbit was also tumbling in space. But why? A century ago, Austrian physicists Lenz and Thirring realized that if Einstein was right, all rotating bodies drag the very fabric of space-time around with them, but the effects are usually too small to measure. In our system, the rapidly spinning white dwarf drags space-time 100 million times more strongly than the Earth would, causing the entire orbit to tumble in space. Our work was published today in the prestigious journal Science, and is another unique exploration of Einstein's general theory of relativity.
Stars are built with the lightest elements in the universe, hydrogen and helium, but they contain an incomprehensible amount of mass. Our sun is made of 2 × 10 to the 30 kilograms of stuff. That's a 2 followed by 30 zeros. That's 330,000 times more stuff than the Earth. So you'd think it'd be a bit of a challenge to throw something around that massive. But there are events in the universe which are so catastrophic, they can kick a star so hard in the pills that it hits galactic escape velocity. Rogue, or hypervelocity stars, are moving so quickly, they're leaving the Milky Way and never coming back. They've got a one-way ticket to galactic Voidsville. The velocity needed depends on the location. You need to be traveling close to 500 kilometers per second. That's more than twice the speed the solar system is going as it orbits the center of the Milky Way. So there are a few ways you can generate enough kick to fire a star right out of the park. And they tend to be some of the most extreme events and locations in the universe, like supernovae and their big brothers, gamma ray bursts. So supernovae occur when a massive star runs out of hydrogen. It keeps fusing up the periodic table of elements until it reaches iron. And because iron doesn't allow it to generate any energy, the star's gravity collapses it. In a fraction of a second, the star detonates and anything nearby is incinerated. But what if you happen to be in a binary orbit with a star that suddenly vaporizes in a supernova explosion? That companion star is flung outward with tremendous velocity, like it was fired from a sling, clocking up to 1,200 kilometers per second. And that's enough velocity to escape the pull of the Milky Way. Huzzah! Onward to adventure. Ah, crap. Please do not be pointed at the Earth. Now, another way to blast a star out of the Milky Way is by flying it too close to Kevin, the supermassive black hole at the heart of a galaxy. And for the bonus round, astronomers recently discovered stars rocketing away from the galactic core as fast as 900 kilometers per second. It's believed that these travelers were actually part of a binary system, and their partner was consumed by the Milky Way's supermassive black hole, while the other was whipped out of the galaxy in a gravitational high-halide scoop. Interestingly, the most common way to get flung out of your galaxy occurs in a galactic collision. Check out this animation of 2 galaxies banging together. See the spray of stars flung out in long tidal tails? Billions of stars will get ejected when the Milky Way hammers noodle first into Andromeda. A recent study suggests half the stars in the universe are rogue stars with no galaxies of their own, either kicked out of their host galaxy or possibly formed from a cloud of hydrogen gas flying out in the void. And they are also particularly dangerous to Carol Danvers. Considering the enormous mass of a star, it's pretty amazing that there are events so catastrophic they can kick entire stars right out of our own galaxy. So what do you think life would be like orbiting a hypervelocity star? Tell us your thoughts in the comments below. Thanks for watching. Never miss an episode by clicking subscribe. And our Patreon community is the reason these shows happen. So we'd like to thank Judy Jackson, Buddy Tatum, and the rest of the members who support us in making great space and astronomy content. Members get advanced access to episodes, extras, contests, and other shenanigans with Jay, myself, and the rest of the team. Want to get on the action? Click here.
On August 17th, something special happened. For the first time, we detected gravitational waves that were coming not from the collision of black holes, but from the collision of two neutron stars. A neutron star is what's left after a star burns all of its fuel and implodes under its own weight. 135 million years ago, in a galaxy far, far away called SGC 4993, two neutron stars were in spiraling, they were rotating around each other. They got as close as the distance between Atlanta and Nashville when they started merging. As they were spiraling faster and faster, they were stretching and squeezing space-time. They produced a gravitational wave signal that kept traveling all the way to us, and then they merged. As they merged, they produced a fireball of gamma radiation. That light also traveled all the way to us. And the residual matter that was left behind started merging in nuclear reactions in this process that's called a kilonova, and they produce heavy elements such as iron and gold. The gravitational waves reached the two LIGO detectors and the Virgo detector. They produce almost imperceptible changes in the length of the three detectors. And that was detected as a gravitational wave signal by LIGO and Virgo. About 2 seconds after the gravitational waves arrived to LIGO and Virgo, the Fermi satellites detected a burst of gamma radiation that was coming from an area of the sky that was consistent with the gravitational waves. Within about 40 minutes, telescopes and satellites all over the world were alerted of this event, and they started their follow-up campaign. And this is going to give us important clues in where heavy elements are formed, how matter, as we know, is formed, in which processes. And this is very exciting because we are really making use of both the gravitational wave and the electromagnetic wave information to learn new things. We have really unlocked this new window into the universe, and we're making the best use possible of it.